we derived the equation of elastic curve and the load displacement curve when the beam is subjected to axial load along with transverse load at the center of the beam. Now, let us write the general expression of this elastic curve when the transverse load is at any place of the beam, that is applied at a variable distance from one end of the column along with the axial load. We will extend this concept for finding the critical load for the continuous beam when it is subjected to both transverse and axial load. Let us take a simple supported one span beam column and do the procedure how to analyze. Here, this is the example of beam column. Here axial load is P is applied and this W is the transverse load is applied. We will have to write the equation of elastic curve, that is our objective, means the general expression of the y value. Now, in this case the equilibrium equation will be for left part of this load, means for this part, from this to this part, it will be one expression, and for the right part of the load the equation of the elastic curve will be different. That we can, how we are writing it, let us see. Okay. If we will take a section at any section at a distance x from this support, from left support, and let at that point the displacement may be y. If we write the equilibrium equation the way we are writing in our previous lecture, the same thing will follow here. We will write the equilibrium equation. Let us this is the part of the beam column. I am drawing it. This is here the load is applied is P, and this is the y, and the load applied here it is again same P, and this is the shear. In this case, if W is acting here at a distance z from right hand and left hand it is L minus z. So, this will be, this reaction will be Wz divided by L, because this is z, and this value L minus z. So, the reaction here for this case it will come W L minus z divided by L. So, here, so this you are writing Wz by L. So, to balance this here, this will be Wz by L. Then if you write, yes, one more thing left, the moment. The moment it is, this is minus EI into y double dash. So, if we take the moment about this point and write the equilibrium equation, this becomes minus EI into d square y by dx square. If we will bring to one side of everything, that we can write plus Py plus Wz by L into x, because this distance is x. If you are taking moment about this point, this load will create a clockwise moment. So, everything I am writing in clockwise direction, that equal to 0. This was this moment, this was anti-clockwise, sign was negative. So, I made everything in the left side of the equation. D square y by dx square plus k square y is equal to minus Wz divided by EI into L multiplied by x. So, here this case we can write the limit that x is greater than 0 and x is equal to x is less than or equal to L minus z. This equation is valid from this to this, from x is equal to 0 to x is equal to L minus z. This up to this only, this equation what I wrote, it is valid. So, because of that I have written this. This is including this point, including this point and also including this point. So, because of that I have written x is greater than or equal to 0, less than or equal to L minus z. Yes. Then similarly we can write this part of this beam column, this part. For this part we will write and this x, let it is a distance x from here. So, this is the section and x value varies from this point to this point. So, you can write here the same way. If we will take a part of this beam column, then if we will write equilibrium equation, it will be like this: EI d square y by dx square plus p into y plus w into L minus z by L into L minus x, this is equal to 0. One thing you should keep in mind, these angles are very small, that it has been shown exaggeratedly, but this angle is very small. Because of that we could write this mx is equal to EI d square by dx square. This is only based on very small deflection theory. So same small deflection theory will follow, and we will write this right part here. If we will write the equation for this right part, and if we will write, yes, this is distance y and this is the applied load, this is P and this is same P, and here this shear force is W into L minus Z divided by L, and this is opposite. So, this is the same thing, same value, same W L minus Z divided by L. Okay. And if we will take the moment about this point, this one, this equation will come, and here this W multiply L minus Z divided by L, that will be multiplied by this distance. So, this distance is how much it will be? It will be L minus x, because this is up to from this to this becomes x. So, the distance left here is L minus x. So, this way you can write, and if you write moment about this point, then this is the equation, equilibrium equation. Then this equation in standard format if you write, it will be d square y by dx square plus k square y is equal to minus W L minus Z divided by EI into L into L minus X, and here this X value is greater than or equal to L minus Z and less than or equal to L. This is the limit of X. Here limit of X is 0 to L minus Z, here L minus Z to L. So this way, in this elastic curve, we wrote the expression for the left part of this load and right part of this load, applied load. So now the solution. The general solution for this is y of x is equal to a sin kx plus b cos kx minus wz divided by pl into x, and for this the general solution is similarly y of x is equal to c sin kx plus d cos kx minus w L minus z divided by PL into L minus x. This we know, this is a particular solution that if when you will substitute in the governing differential equation, that will satisfy. This exercise already we have done. Now this is the two solution for two part of this beam. When the x varies from 0 to L minus z, that is when x is greater than or equal to 0, x is less than or equal to L minus z. So this is the equation. And when x is greater than or equal to L minus z and less than or equal to L, this is the equation. Now next objective is to find these constants C, D, this A and B, that we will have to find it out. Here we will have to use other boundary condition. At this point, this is the let y value. If we use this equation is valid from x is equal to 0 to x is equal to L minus z. So if we need to find y value at L minus z, this equation will be satisfied. And for finding the y value, if we use this equation which is valid for x is greater than or equal to L minus z and less than or equal to L, then also you will get the same value. So we can write another boundary condition to find these constants. The boundary condition, you can write y value at x is equal to 0 is equal to 0 and y value at L is equal to 0. So this y at x is equal to 0 is equal to 0. This at x is equal to 0 satisfies this equation. Means if you see the range, x is greater than or equal to 0, x is less than L minus z. So this is satisfied. So if you substitute here in this equation this boundary condition, it will come b is equal to 0. And next one is the displacement at L is equal to 0 is 0. This thing we can find it out from this equation, because this equation is satisfied when x value is greater than L minus z and x is less than L. So for this, if you substitute this, you get C is equal to minus D into cot K L. This is the thing. And we can get another boundary condition is y of L minus z. If we will find through this equation, because x value also satisfied when x is equal to L minus z. This y value at L minus z, if we will use the equation which is derived for the left part of the beam column, means left part of the loading, the point load applied, for that it is satisfying. So this will be equal to y of L minus z of the equation which is valid for the right part of the beam column, means right of the applied load. So this will give one equation, and another thing, the slope also there will be same. You can write here that y dash L minus z at left is equal to y dash L minus z right. So left right I have written means this equation is for left part, this is I am writing here left, and this equation is for right part. Right part means right of the loading, W is the load applied, and the elastic curve for right of this loading is satisfied by this equation, because the equilibrium equation is derived accordingly. From the equilibrium equation only we got this equation. This was the equilibrium equation, finally we got this equation. Similarly, for the left part we start the equilibrium equation and we wrote the final equation of this deflected shape, this elastic curve is this. So this, because of that I am writing here left and right, there is nothing to be confused. Okay. If you use this equation, this will be in this format: a sin k L minus z minus wz divided by PL into L minus z is equal to C sin k L minus z plus d cos k into L minus z. You can write here like this, and minus of W L minus z divided by PL into this is z. This z comes, this was L minus x, isn't? This is L minus x. If you substitute x is equal to L minus z, this becomes L minus z. So L minus L plus z. So this becomes z. Because of that, this has come z. This has come z. This is L minus z. So this comes L minus L plus z. So if you simplify this equation further, this comes a sin k into L minus z yes is equal to d into cos k into L minus z minus cot k L into sin k L minus z. We are substituting L minus z in place of x. that exercise we have done. Similarly, if we use the slope, continuity of the slope, whatever the slope we will find by using left side equation, and the same slope we will get if we use the right side of the equation. So that will be, if we will write the equation, that will come in this will come AK. You will have to differentiate this equation once, and you will have to substitute x is equal to L minus z. So that will come AK into cos kx minus bk into sin kx minus wz divided by PL into C is equal to CK cos kx minus D K sin kx plus W into L minus Z by PL implies A K cos kx minus W Z divided by PL, because this B becomes 0 because of that. So this has come equal to minus D cot KL, because D value, if you will see, C value we have got minus D cot KL. So minus D cot KL multiplied by K into cos kx minus D K sin kx plus W L minus Z by PL implies K cos K into L minus Z minus WZ divided by PL is equal to minus D K cot KL plus cos K into L minus Z minus dk into sin K into L minus Z plus W of L minus Z divided by PL, that it is equation 1 and equation 2. And we will have to solve these two equations. These two equations, two unknowns. Unknowns are A and D. If you will solve it, you will get in equation 1 and 2. We get A is equal to W sin kz divided by pk sin kl. This is A, V value is equal to 0, we know. C value is minus W sin K into L minus Z divided by Pk into 10 KL, and this D value is W sin K into L minus Z divided by Pk. This is sin K x, so sin L minus Z has come. So this is the four constants. Okay. Now the final the final equation of the elastic curve is the final equation of elastic curve is yx is w sin kz divided by pk sin kl multiplied by sin kx minus wz divided by pl into x, and this x is greater than equal to 0 and less than equal to L minus z. So, this is the equation within this range. This is the elastic curve, and y of x is equal to w sin k into L minus z divided by pk sin kl into sin k into L minus x minus w L minus z into L minus x divided by PL. So, this is for x is greater than equal to L minus z and it less than or equal to L. So, this is for left part, this is the left part of the loading, and this is the right part of the loading. This expression is the right part. Now, our next objective is to find the slope at the center, the slope at the support. Let us find it out, what expression we are getting. The deflection at x is equal to L by 2 and z is equal to L by 2. I mean, when the load is at center, when z is equal to L by 2 means load at center of beam column. See, z is equal to L by 2 and x is equal to L by 2. We are interested to find y value when x is equal to L by 2 and z represents the position of the loading. Let me see again, I wish to show you. This is the z value, this you see, this is the z value, and when z value is equal to L by 2, the load is at the center. So, we are finding it out, y at x is equal to L by 2, this becomes w sin k L by 2, k into L by 2 divided by p k sin kl into sin kl by 2 minus wl divided by 2pl into L by 2. If you substitute in this equation at x is equal to L by 2, you substitute, we get this expression. You can use any equation, any of this equation you can use, because x value is defined and z value is defined. So you can substitute here and you can get any one equation you use, and you will let us use in this equation, and we can get this expression, and this value will be W by 2 pk into 10 kl by 2 minus WL by 4p. So this becomes W by 2 pk by 10 kl by 2 minus kl by 2. So implies y is equal to WLQ divided by 48 EI into 3 of 10 U minus U divided by UQ, where this U is equal to KL by 2. If you simplify this expression if you simplify, it will come like this. We have expressed y value in this format because we have expressed in such that this part of this expression, this is the deflection at the center when the beam is subjected to point load W. When deflection, when only W acts and this is the factor which amplify the deflection. So this is the amplification factor, one factor because of the axial load. You can write here, this part is influence of longitudinal force. Longitudinal means axial force, yes. Longitudinal force means axial force. And you can write finally this expression implies y as, how we can write? We can write is WLQ divided by 48 EI multiplied by eta into U, and this is 3 of 10 U minus U divided by UQ. Let us calculate the slope of the deflected curve at the end of beam. Slope of deflected curve at the end of beam. Deflected curve means this is the elastic curve. We will have to find slope at the end. Slope at the end you can find out by making dy by dx at x is equal to 0 and the load is applied at the center. Load is applied at the center means z is equal to L by 2. So if you will do it, you will get WL square divided by 16 EI multiplied by 2 times 1 minus cos U divided by U square into cos U. So this is similarly the effect of axial load. This is the factor which is due to the axial load. So this is the effect of axial load. So what will be the maximum theta value? Theta max is at x is equal to 0 and z value is equal to L by 2. So the maximum slope is WL square by 16 EI multiplied by, I am writing this as phi of U. This is one interesting thing I forgot to tell. What is this factor? This factor is the slope produced by lateral load W acting alone at the center of the beam. The maximum bending moment we can calculate. Maximum bending moment is, you can calculate, the expression is minus EI into d square y by dx square. You will have to calculate, where it will be x is equal to L by 2 and the load is also at the center. Center means Z is equal to L by 2. If you will find it out, if you will differentiate the elastic curve twice and substitute x is equal to L by 2, Z is equal to L by 2, then you will get the expression as WL by 4 multiplied by 10 U divided by U. So, you should not get confused which elastic curve you to use. Here you can use any elastic curve, left part or also right part, anything you can use. This part you can use, also this part also you can use, because you are substituting this x value and z value, so nothing to be confused. So, both the equation that will give the same value.